Now we'll look at the particular numbers in the equation of a line. We have to kind of review a little bit. We know we did a little bit in the previous pages, but now we'll get more into detail about it. We now know that the least squares regression line is the line that best fits the data. It gives the most accurate predictions because it has the smallest overall prediction error. More specifically, it has the smallest sum of the squared errors, like we saw on the previous page. Now we focus on the numbers in the equation of the line and discuss what they tell us about the relationship between the explanatory variable and the response variable. The general form of the equation of a line now we'll look at. Here are some of the equations of lines that we have used in our discussion of linear relationships. First, the predicted distance we saw was about how far can someone see based on their age. 576 minus 3 times the person's age. And I think we even specified, just to get it more looking like the equation of a line, we usually see mx plus b. But a lot of times with regression lines, they switch them. You'll see the number without a variable first, and then the number with a variable. So they wrote 576 minus 3 times the person's age. We'll just say that the person's age is x. So something like that. And then another example might be predicted height is 39 plus 2.7 times your forearm length. That's kind of interesting. In that case, 39 is the y-intercept or the constant term that does not have a variable attached, plus 2.7, that's the slope, times your forearm length, that would be like your x value. And the third example, predicted monthly care insurance premium, 97 would be your y-intercept, and then the slope is minus or negative 1.45 times the number of years of driving experience, that would be your x value. So those are just 3 examples. Notice that the form of the equations is the same. In general, each equation has the form y equals a, some number, some constant number that does not have a variable, plus b times x, some number, the slope. When we find the least squares regression line for the data set, a and b are determined by the data. The values of a and b do not change, so we refer to them as constants. The meaning of a and b in the equation of a line. In the equation of the line, the constant a is the prediction when x equals 0. It's called the initial predicted value, or as you've seen in algebra classes, the y-intercept. But here we'll use different language because this actually represents something in our context. The initial predicted value in the graph of the line, yeah, it's the y-intercept. In the equation of the line, the constant b is the rate of change, we call it, or the slope. Either way, same difference. In a graph of the least squares line, b describes how the predictions change when x increases by 1 unit, or the slope, right? As I go larger and larger x values, am I going up or down on the y-axis? And how quickly? More specifically, b describes the average change in the response variable when the explanatory variable increases by 1 unit. We can write the equation of the line to reflect the meaning of a and b. Predicted y equals a plus b times x. The predicted y value is equal to the initial a is the initial value plus the rate of change b times x. Or in other words, the y-intercept plus the slope times x. The meaning of a and b in the graph of a line. This is a little bit of review here. So in this line, in this example that they show in this graph, the y-intercept is 1. Like I said, that's the initial value when x equals 0. When x is 0, y is what? That's what the initial value represents, or the value of well, they're using an a, I should use an a. 1. So because that's because there's a point on the line at 0, 1 right there. And then the slope, or the value of b, slope, it tells you as I go to the right 1 unit, how high am I going up, or how far down am I going? In this case, yeah, they're going up because it's sloping upward, but I'm going up b units, whatever b is. It's a number, and in those 3 examples above, they're specific numbers, but we'll see them in all the different examples coming up. So yeah, in algebra class, you may have learned that the equation of a line is y equals mx plus b. In this form of the equation of the line, m is the slope and b is the y-intercept. As we noted above, a statistician will tend to use b as the slope, just to make it maximally confusing for us. Thanks, guys. Statisticians, instead of using b to represent the y-intercept. This can be confusing. In this course, we will write the equation of the line in the form y equals a plus bx. And that's because when you use technology to figure out what the line is, they will say that. If you use technology, either a graphing calculator or an applet or StatCrunch, they'll say a is blah, 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 whatever number, B is blah, 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 whatever number, and you got to remember what those represent. So from now on, I'm not going to say M or B. I'm not going to say M is the slope, B is the y-intercept. I'm going to be saying A is the y-intercept or the initial value, B is the slope or the slope or the rate of change. The two forms of the line are equivalent despite the confusing use of B to represent two different things. I don't know why we can't just all get on the same page and use the same thing. Am I right?